Muller's blunder, the mistake that cannot be stopped. I know you really don't like the title of this video, Muller's blunder. You're probably thinking, poor Muller, whoever he was. He deserves better. We should celebrate successes instead of pointing out failures. Okay, I don't feel good about pointing out other people's mistakes. We all make mistakes. But mistakes are important, and today we will find out about a big one. One misconception that people have about mathematics is that, unlike medicine, mistakes in mathematics are not very consequential because mistakes can easily be corrected, and other mathematicians are always looking for these mistakes, so they are easily found. If you're a surgeon and you remove the left eye when you were supposed to remove the right eye, then that's bad. You can't undo a mistake like that. But math is much more like the left eye, right eye example than you might think. Mistakes in math could be fixed, but they won't be fixed if they are never found. And mistakes mathematicians make are hard to find. This is a story about a mathematician who was the right person at the right time and the right place to make a real difference. And in a way, he did make a difference, just not in a good way. It took years and years for mathematicians to find the better method, the one the original mathematician almost found and should have found. And by then, no one cared. The moment had passed, and the need was gone. After nearly 70 years, the Muller's original method is still being taught, and the better algorithm is all but forgotten. Muller's blunder is like a juggernaut, a mistake that cannot be stopped. Here's a picture of David E. Muller, professor at the University of Illinois. He was a mathematician and computer scientist at the golden age of computer science, the 1950s. This was a time when we were figuring out how to solve problems on a computer. Computers were slow, storage was limited, and algorithms had to be clever. Muller had several famous discoveries and inventions that were written up in Wikipedia. He was the Muller of the Reed-Muller code in data transmission error and detection. He was the Muller of the Muller C element for asynchronous computing. He was also the Muller of Muller's method, which we will get to shortly. I'm not really sure what the first two things on this list are, and honestly, I don't really care too much, but let's just say that Muller had a remarkable career with many accomplishments. Okay, most students would have come across Muller's name in his method for computing the roots of a function using 3 points and a parabola. I'll describe this method in the blunder in a little bit. This method is still taught in many universities. I found at least a dozen universities that have lecture notes associated with this method. And there are certainly many more universities that teach it but don't put up lecture notes. One unusual thing that you'll notice is that many of the lecture notes have the name misspelled with umlauts, and I'll talk a little bit about that odd feature. So why the umlauts? Why Muller instead of Muller? Well, the names do get confused from time to time, but Actually, this only happens with Muller's algorithm. For Muller's method, it doesn't happen with the Reed-Muller code. It doesn't happen with anything else. The reason why is people copy-paste references without verifying anything. Once one person gets it wrong, it's copied by 100 others. Muller's paper on the original method was hard to follow. People preferred to read secondary sources, and many of those secondary sources had the name spelled incorrectly. And then maybe a combination of the two. Misspelling was in the American textbook Numerical Analysis by Burden and Fairs. This one textbook probably was the root cause of most of the misspellings that you see out there. And it's a bizarre mistake for an American to make, but I'm not going to dwell on this subject. We're going to go on. Okay, the problem that Muller was trying to solve was finding the root of a function. Let g of x equal a function. You're trying to find out where g of x equals 0, so that's the green dot on this graph. There's a lot of ways to do it. A standard way, classic way, is Newton-Raphson method. You pick a point on the curve, and then you find a tangent line. The blue line is a tangent line to that point, and you use that as a proxy for the yellow curve. So you find the tangent line using the derivative of the function as the slope, and you solve for the red dot by finding where L of x is equal to 0. You get this iconic formula for xn plus 1. Now, one thing to note here is that the convergence of Newton's method is famously quadratic, which means that the errors go down very quickly. They square each time. But you might be surprised that Newton-Raphson method has some drawbacks. It requires a separate subroutine to calculate the derivative. It requires 2 subroutine calls per each iteration, one for the function and one for the derivative. And some derivatives are more trouble to calculate than it's worth. This looks maybe a little bit silly, but examples like this can happen. And methods that just use the function without the need for a derivative could be more versatile and perhaps faster. Okay, this brings us to the next method called the secant method. The secant is just a line that goes through 2 points on a curve. It's kind of like a tangent, but not as exact. When the 2 points are closer together, they're more like a tangent. So we calculate a slope using the 2 points, and we calculate a line using the point slope method. The formula for the secant is almost exactly like Newton's Raphson method, except that you're using the m, which is a numeric derivative, instead of the actual derivative. Secant method famously doesn't converge quite as fast as Newton's method. It has golden ratio convergence. Phi, the golden ratio, is 1.62. This means that this method will actually be superior to 3 iterations of secant method, or superior to 2 iterations of Newton-Raphson method, or 6 iterations of the secant method would be superior to 4 iterations of Newton-Raphson. So if it takes 4 iterations for Newton-Raphson to converge, that would be 8 function calls. But the 6 iterations of the secant method would be 7 function calls, 6 plus 1, 1 for the first iteration. So 7's less than 8. So sometimes secant method would be faster. That's why computer scientists were really excited about this method. So this is typical for mathematicians. Now that we have a method that uses 2 points, can we generalize it to something that uses 3 points or k points? That's what mathematicians like to do. So now that we have 3 points, the question is, can we use a third point? And if so, how would we use it? And this was the question that Muller was trying to answer. His idea was, well, 3 points, you can fit a parabola through 3 points, and you can solve a quadratic equation. So there are 2 parts to this method. First part is that you have to do some curve fitting. This is straightforward. This is something that's been known about. You take 3 points, you fit a curve to it. And then the second part is also fairly well known. Use the quadratic equation to find the root. And that was basically his idea. Now for curve fitting, there's a right way and a wrong way to do it, and you don't want to use this form. And the reason why is you'll make your life miserable by using this. You will make the math much simpler if you use the Taylor series expansion. This is something that has been known all the way back to the time of Isaac Newton. You want to use the fact that x minus xn is small, and that is a crucial thing to understand the blunder that comes up later. But there's also another advantage of this. We know the parameter a0 is just y sub n. So it's really just 2 parameters we have to solve for. Okay. Now we want to find the zeros of the blue curve. This is the function. We already have the values of a1 and a2 solved. Now we're just finding the value of x that would make this 0. That's the red dot. And this form of the quadratic equation might look a little bit different to you. You can sit down and work it out and say, oh yeah, it's exactly the same thing. The advantage of this way is that we can find the exact root. We don't have to compute 2 of them. The one that we want is the one that has the same sign as the sign of a1. So, much of the paper that Muller wrote was on this convergence. And this is actually the good part of the paper, by the way. He was able to show that convergence was defined by this parameter alpha that's 1.84. That means 8 iterations of Muller's method is superior to 7 iterations of the Newton-Raphson method. To put in context, it takes 10 iterations of the secant method, and it would not be as good as 7 iterations of either Newton-Raphson or 8 iterations of the Muller's method. So Muller's method will save a step, save an iteration over secant method if secant method requires 5 or more iterations. It's a good thing to know. Okay, now we're getting to the actual blunder. Suppose we're trying to find the root. We have a1 and a2 already calculated. Now, at this point, look at that quadratic term. How big is it? Yeah, that term does us no good. We might as well just drop it. It's like noise. It's so small. And that simplifies the root finding enormously. This is Muller's missing model. All you have to do is solve this linear equation. And you get this formula that looks an awful lot like the secant method or Newton-Raphson. The difference is that a1 is like the slope term. Let's look at this in a picture form. Muller's missing model is equivalent to applying Newton-Raphson's method not to the original function g of x, but to the quadratic approximation p of x. It's the orange line. The orange line is tangent to the blue curve, not the yellow curve. And you find the red dot by finding where the orange line intersects the axis. You're probably thinking, this sounds like an approximation of an approximation. And it is. Let's be clear about that. Your intuition says that this is always a bad idea. It sounds like a photocopy of a photocopy. But your intuition is misleading you here, because this isn't how asymptotic approximations work. The errors don't really add in the way that you might think. The overall error is dominated by the dominant error, the error that is going to zero least quickly. Adding subdominant errors is effectively like adding zero. So an approximation of an approximation, in this case, is just as good as the original approximation. So the convergence of Muller's missing method, it's the same. It's the same as Muller's original method, 1.84. And the reason why is the difference between these two models is smaller than the error associated with convergence of either model. So let's look at major steps, reviewing them. For the original method, we have to compute A1, we have to compute A2, we have to compute the discriminant, the thing under the square root. We have to verify that it's positive. And if it isn't, we have to do something else, like maybe regular secant method. And then the last step, and probably the most time-consuming for a computer, is to compute the square root. Now let's compare that with Muller's missing method. Here we have to compute A1, and we're done. That's it. It's much, much simpler, much less computation. Okay, now just go through this very quickly, the curve fitting. And the curve fitting is not any different between Muller's missing method and Muller's original method. They're really, this part's the same, except I'm not going to bother to compute A2. So you start off with this functional form. We're going to plug in some points. And we're going to solve for A1 and A2. It'll be 2 equations and 2 unknowns. So let's plug in the lagged values. And we come up with these lagged differences. And let's bring all the constant terms to one side. And notice at this point that these differences are kind of going in the opposite way that we typically do it. We like to think about the most recent number minus the lagged number. So we'll multiply by -1 to get it into the canonical form. That form puts a minus sign on the squared terms. And then we'll use, we'll just clear the A2 terms by cross multiplying. The first one is multiplied by the del x lagged 2. The second one is del x lagged 1. And we get this formula. And this formula is in Wikipedia and a lot of other sources if you want to find it. So the examples will show are ones that probably could be computed best with Newton-Raphson, but we'll use secant method and then the Muller's missing method. This is a simple cubic, very easy to solve. It comes up in trigonometric problems. The fixed point formula is to get the first 2 points, which we need. We need 2 points. So first point, s over 3, and then use this fixed point formula to get x1. Let's go to the spreadsheet and see how this method works. Okay, first part, we're going to just do the secant method. I'll go through this really quickly because it is, it's something everybody has seen before, and it's just not worth spending a lot of time on this. We're going to use that fixed point formula here to get the first 2 points. And then we'll copy the x over the y. This is the part where you have to remember what the formula is. 3x minus 4x cubed minus the parameter. I have to put the dollar signs there on the parameter. And then we compute delta x, delta y, the slope. It's very standard. And the adjustment is just minus the y value divided by the slope. And we just add the old x value and the adjustment to get the new x value. Bring that down. And then calculate some statistics here on the right. The natural log of the absolute value of the adjustment kind of measures, we'll use that to compute the ratio. The ratio is, we're going to check to see if that ratio is close to 1.62, and it's kind of close, but maybe not. This column, it relates to that ratio of this Fibonacci number. It's basically the sum of the previous 2 errors is equal to the next error. Okay, so now that we got that, let's copy that over. That'll be the first step of Muller's missing method. We have to, by the way, we have to get the first 2 values again. Okay, now that we got that, we have to find del x lagged 2 times. This is the wrong cell. I got to go down one more. Okay, del x minus 2 terms, and then del y lagged 2 times. And the formula here, del x times del lag 2 squared minus del y times y lag 2 times del x squared. In the numerator, denominator is del x, the previous term, and then del x lag 2 all multiplied together. Calculate the slope. This is an important point. The slope should be about the same. I should get a number very close to 2.63 or 2.64. Yes, it's very close to the same number. It is different, but it should be very close to the same number. And the adjustment should be very close to the old adjustment, but actually it's a couple of digits different in small digits, important digits. And when we when we use the new adjustment, we'll save a whole iteration. It's a nice thing. That's all you had to do to make the secant method faster. So yeah, the ratio, you can kind of see it over there. It's supposed to be 1.84. It kind of is in the neighborhood of that. But the main thing to note is how quickly it converges. This number, by the way, the column called Fibonacci, that should be roughly, it should be that each error is about the sum of the natural logs of the 3 previous ones. That's why it's very fast. It converges quickly. So this is just comparing how quickly secant method and Muller's missing method converge. In each case, it's about 1 iteration faster with the Muller missing method. You can see it's 1 whole iteration faster every time. Well, if you choose a very small number for the parameter and it converges too quickly, you won't see a difference between secant and the other method because it converges too quickly. You just don't see the benefit. You need a little bit bigger number, something that converges a little slower, and then you start seeing a difference between these methods. Okay, let's do another example. Another example will be quicker because we don't have to spend time coding. Here's a problem that uses, this is like a 5th root problem, and here's the fixed point formula for getting the first point. A over 5 is a decent first guess for most small values of A. So let's go to the spreadsheet and see what this does. Now in this case, I'm not going to type in all this stuff. I'm just going to copy the entire sheet over to a blank sheet. Change the parameter name to A. Change the initial points and the function name and a function definition. And in fact, I'll just copy the function over to save time, because I don't want to spend a lot of time typing all this in. So I have it typed over here. You can see the function. All right, copy this function. It's 5x plus 10x squared plus 10x cubed plus 5x to the fourth plus x to the fifth minus the parameter. Once I put in the function, it will compute. There's nothing else to do. And once again, you will see that this Muller's missing method converges one whole iteration faster than the secant method for a completely different problem. It will almost always converge faster, as long as it takes a few steps to converge. It will converge faster. We're just comparing how quickly, how the adjustment here, you can see it converged one whole step faster. Here we're choosing a larger value of a. That'll make the secant method converge much more slowly. But the Muller's missing method converged reasonably quickly here. Now 2 is kind of an unfortunate first value, because the initial guesses are way out of range, so it just wastes a lot of time getting going. But despite that, and you see this method converged, this case, 2 iterations faster than the secant method. I was going to bring it down and I realized, wait, it's already converged. There was no need to bring it down. Okay, can you generalize Muller's method to include more points? Like, we have 3 points. Could we do 4 points, 5 points, or k plus 1 points? Yes, and it's straightforward to do, but it might not be worth the effort. I'll just go through it quickly. The standard method of curve fitting is that you would set up a matrix M that's these lagged values of x raised to powers, and then the y vector is the lagged values of the y differences, and the A is the thing you're trying to solve for. These are the parameters of the polynomial. But the only one we care about is A1. So you just solve for A1. And you plug it into your formula and you're done. So the convergence properties, in this one would be, you can see how much faster it would converge in general. So it gets closer and closer to 2. However, it might not be worth the trouble, because computers can only compute to 16 decimal places. And remember, you have to do one step of the k equals 1 version, and to do the one step of the k equals 2 version, to do one step of the k equals 3. By that time, you probably converged anyway. So, yeah, what's the point? But if you compute something to 1,000 digits, this might be the method. Yeah, you might seriously want to think about it. All right, time to close the spreadsheet. Thank you.